In this video, we continue with Chapter 2.5, and our learning objective is to find the steady-state matrix of an absorbing Markov chain. So let's learn about what an absorbing Markov chain is. So consider a Markov chain with n different states, S1 through Sn. The ith state, Si, is an absorbing state when, in the matrix of transition probabilities, this is also known as our stochastic matrix or a Markov matrix, one of the diagonal entries, Pii, is 1. That is, the entry on the main diagonal P is 1, and all the other entries in that column are 0, right? Because to be a stochastic matrix, the columns all need to sum to 1. So an absorbing Markov chain has the two properties here. Property 1, the Markov chain has at least one absorbing state. You can have multiple absorbing states. And property 2, it is possible for a member of the population to move from any non-absorbing state to an absorbing state in a finite number of transitions. So remember, the population is whatever we're studying. It doesn't necessarily have to be people. It could be money in different bank accounts, as we saw in an earlier example, or animals, or any other objects that we're moving around through these transition matrices. So the transition matrix P here below corresponds with the diagram at right. So the columns correspond with where we are moving from, and the columns correspond with the state that the population is moving to. And so we can verify that each column sums to 1. And then we see here that S1, 40% stay with S1 and 60% leave to go to S3. We can see in S2, everything that makes it to S2 stays in S2, and then 50% from S3 move into S2 with each transition, and 50% stay within S3. And so we see in that last row the 60% coming from S1 to S3, and the 50% staying in S3. So in this matrix, the second state, represented by the second column, is absorbing. Moreover, the corresponding Markov chain is also absorbing because it's possible to move from S1 to S2 in 2 transitions, and it's possible to move from S3 to S2 in 1 transition. So we meet all of the criteria, both properties, to be an absorbing Markov chain. Let's look at a couple more examples. All right, the top matrix P has 4 states, and so we see here the second state is absorbing because everything that makes it to S2 stays in S2. But can you move from states S3 or S4 to S2? You can't. So we say the corresponding Markov chain is not absorbing because there's no way to move from state S3 to S4. And just to make sure everyone is seeing, the 1 here on the diagonal in S2 corresponds with the 100% in this cycle in S2. So anything that goes from S1 to S2 stays there. So that's why we say S2 is absorbing. There's a third example also with 4 states. So we see in our fourth example, there are actually 2 absorbing states, S2 and S1. Notice they both have 1s in their diagonal entries, and all other entries are 0. And if we check out the diagram, we see here S4, everything that makes it to S4 stays there in that cycle, and same with S2. So we have some 100% or 1 probabilities there. So in this case, the corresponding Markov chain is also absorbing because it is possible to move from either of the non-absorbing states, S1 or S3, to either of the absorbing states, S2 or S4. So let's take a look at another example. We are going to find the steady state matrix of the absorbing Markov chain with a matrix of transition probabilities P here. So remember, we think about the steady state matrix as X with a bar at the top. And we are going to be finding matrix X bar such that our transition matrix P here multiplied by X bar gives us back X bar, Or in other words, we can say 0.6, 0.3. So just recopying matrix P here. Multiplied by some column vector, x1, x2, x3, is going to give us back out x1, x2, and x3. And then we also know that x1, x2, and x3 have to sum to 1 because this is a stochastic matrix. Oh, I put a 0 there. Typo. I meant to write 1. All right, so let's head into our linear system. So we're going to use the coefficient matrix here and the values to write our linear system. All right, so in the first equation, we are going to have 0.6 x1, write it out. We'll have plus 0.3 x3 equals x1. So that is going to transition to 0.6 x1 minus x1. So we're going to end up with a negative 0.4 x1 plus 0.3 x3 equals 0. All right, let's write the remaining rows and then we'll translate them. So the next row is going to be 0.2 x1 plus x2 plus 0.6 x3 equals x2. And I'm just getting these values from our multiplication here of p times x bar equals x. So I'm using the coefficients from matrix P and the values x1, x2, x3 to represent x bar, our steady state matrix that we're working to find. And then our last row here is going to be 0.2, or our second to last row, x1 again. There's no x2s there, and then plus 1 x3 equals x3. And then our last row here is x1 plus x2 plus x3 equals 1. Okay, so this matrix is going to, well, before we make the matrix, we'll simplify and get zeros for the top 3 solutions. So then in line 2 here, we're going to subtract x2 from x2. So we get a 0 in there, so we'll have 0.2 x1 plus 0.6 x3 equals 0. And then we have 0.2 x1 again in the third row. And then we're going to get minus 0.9 x3 when we take x3 from the 0.1 x3. That's going to equal 0. And then we'll have x1 plus x2 plus x3 equals 1. All right, let's go ahead and put this as a matrix into Simpy and reduce it. So we could write it right now in matrix form. It's going to be negative 0.4, 0, 0.3, and we'll augment it with the solutions. Our second row is going to be 0.2, 0, 0.6, 0. Our third row is 0.2, 0, negative 0.9, 0. And our last row is 1, 1, 1, 1. So let's go over to Simpy, enter our matrix, and reduce it. Let's see, I'll call this P equals, it's really P augmented, but that's okay. We'll still call it P. And then our values from the top row are negative 0.4, 0, 0.30, values from the second row are 0.20, 0.60. Our values in the third row here are 0.20, negative 0.90. And our last row is all ones. So we can type P and enter to verify our matrix P is a match for what we hand wrote over here. And now let's reduce this. So we will do P dot RREF, put our function in parentheses here, and then in brackets we'll put our 0. And so we see here are our solutions. So we get 0, 1, 0 as the solutions for x1, x2, and x3, respectively. So after RREF, we get x bar equals 0, 1, 0. We can say x1 equals 0, x2 equals 1, and x3 equals 0. So remember, the steady state is what we expect to happen after many, many powers of P multiplied by the initial matrix. So this is the limit that we expect our Markov chain to go to. All right, in the next section, we're going to be looking at some applications of matrices.